welcome to another module in this massive open online course. So, in this module we are going to start on a new concept, a very important concept in fact in analysis of signals and systems known as the Laplace transform. So, we are going to start looking at various aspects of the Laplace of the Laplace transform. And in fact, this is going to be one of the first transforms amongst the many transforms that we are going to be looking at, and basically this gives us what is known as a transform domain representation. This gives us a transform domain representation of the system, and this is a convenient representation of for signals as well as LTI systems. It gives us a convenient representation for signals as well as for LTI systems, and this can be employed for the analysis and to obtain. So, it can be employed for analysis and also to obtain valuable insights regarding the performance and behavior of LTI systems for various signals. Okay. So, this can be employed for analysis, for a performance analysis, as well as and to obtain valuable insights into behavior of signals and systems. So, it can be used for analysis and to obtain insights into the behavior of signals and systems. So, let us look at the definition of the Laplace transform. Which for convenience we can abbreviate as LT. So, the LT is defined as XS for a signal, XT is defined as minus infinity to infinity, XT e raised to power minus XT. Naturally, this is a function of S, where this S equals sigma plus j omega. This is a complex value. So, S is complex value. Okay, so, XS is the Laplace transform of XT. Okay, XS and XT form a signal and Laplace transform pair. Okay, so, XS equals XS equals Laplace transform of XT. Okay, and this is also represented by XS, the Laplace transform of XT, that is the calligraphic L denotes the Laplace transform, or that XT and XS form a signal and Laplace transform pair. This indicates that they form a, this double sided arrow indicates that they form a signal slash Laplace transform pair. Okay. So, the Laplace transform, so this is the definition of the Laplace transform, that is x s equals integral minus infinity to infinity x t e raised to minus s t dt, and the signal x t x s is the Laplace transform of the signal x t, and the signal, and these form a signal and Laplace transform pair. And this is also known as the bilateral Laplace transform, because it uses an integral from minus infinity to infinity. Okay. So, this is also known as a, to be more precise and without ambiguity, to avoid any ambiguity, when we say Laplace transform, we will simply mean the bilateral Laplace transform, that is integral from minus infinity to infinity. Now, an important concept associated with the Laplace transform is what is termed as the ROC, or region of convergence. Now, what is this concept of ROC? This simply describes, okay, this simply describes region of the S plane, or basically range of values of S for which the Laplace transform exists, or the integral for which the Laplace transform exists, or Laplace transform integral converges. Okay. So, this has to converge. Okay. Correct. For instance, let us understand this. So, this basically describes a range in the, or a region in the S plane, which I am going to show you, which I am going to define and demonstrate shortly. That is, it is a region in the S plane, or basically this characterizes the range of values of H for which the Laplace transform for a given signal x t converges. Okay. Let us examine this using an example. For instance, let us say my signal is x t equals e power minus alpha t u t, and x s then becomes e power minus alpha. Let us further assume that alpha is real, alpha is a real quantity. So, this is e power minus alpha t u t e power minus s t dt, because u t is non-zero only for t greater than or equal to 0. So, this integral can be written equivalently as e raised from 0 to infinity e raised to minus alpha s plus t dt, which becomes e raised to minus s plus alpha t over minus s plus alpha between 0 to infinity. Now, look at this, we have to evaluate e raised to minus s plus alpha t as t tends to infinity. Now, this becomes 0, but only under the condition s plus alpha is greater than 0. So, e raised to minus s plus alpha t at t as t tends to infinity is 0, decays to 0 only if s plus alpha is greater than 0. So, this is equal to, we can write the 0 minus, of course, minus this minus 1 over s plus alpha 1 over at t equal to 0, this is 1 minus s plus alpha. So, this converges to 1 over s plus alpha only if e raised to minus s plus alpha times t tends to 0 for t tends to infinity. This implies, which implies that we need the real part of s plus alpha must be greater than 0, which implies, which in turn implies that the real part of s must be greater than minus alpha. and therefore, this is the region of convergence, this is the ROC. Okay. And therefore, the Laplace transform of e raised to minus st ut is given as 1 over s plus alpha, but this exists only if real part of s greater than minus alpha, and this is therefore the ROC or the region of convergence. Okay, this is your ROC or the region of convergence. Okay. And this can be represented, this ROC can be represented in the S plane as follows. So, in the S plane, this can be represented, S plane representation of the ROC. So, the ROC can be represented in the S plane as the follows. So, the S plane simply contains the real part, that is sigma on the x axis, and the imaginary part, that is j omega on the y axis. Okay. And we have, let us say this is minus alpha, okay, considering alpha to be greater than 0. This is basically your minus alpha, okay, and the ROC is basically this entire half of the S plane, which is basically real part of S without, and it does not, remember, it does not include the line corresponding to minus alpha, because real part of S is strictly greater than minus alpha. So, this is real part of S greater than minus alpha. So, this is your j omega axis, and real part of S greater than minus. So, this sigma, this is the real part of S, this is the imaginary part of S, and this is basically real part of S greater than minus alpha, this is the ROC. So, this is the ROC representation for, so this is your ROC S plane representation for e raised to minus alpha t ut, this is the ROC, and this is basically the ROC or the region of convergence for the signal above. Now, let us look at something slightly different. Okay, let us consider a slightly different signal, which is considered now xt equals minus e power minus alpha t u minus t. This is different because it's non-zero if t less than or equal to 0, okay, because u minus t is non-zero only for t less than or equal to 0. Okay, xt equals e raised to minus alpha t u of minus t. This is non-zero only for t less than or equal to 0. Okay. Now, so this signal, so while the previous signal was e power minus alpha t ut, this is minus e power e raised to minus alpha t u minus t, which exists on the left side. Alright, so this is a left handed signal, okay, that exists only for t less than or equal to 0. Okay. Now, if you look at the Laplace transform of this signal, once again we perform minus infinity to infinity minus e power minus alpha t u minus t e power minus st dt. Now, note that this is can be equivalently written as, now since this is non-zero only for t less than or equal to 0, so this can be equivalently written as minus infinity to 0 minus e power minus once again s plus alpha t dt, and the integral is minus 1 over minus s plus alpha evaluated between the limits. This time it is minus infinity to 0, which is basically now, I am sorry, I have to also write e power minus s plus alpha t, e plus e raised to minus s plus alpha t. Now, e raised to minus s plus alpha t evaluated at 0 is 1. So, this becomes 1 over s plus alpha minus. Now, e raised to minus s plus alpha t as t tends to minus infinity is 0. Now, this converges, that is e raised to minus s plus alpha t tends to 0 for t less than 0 only if the real part of s plus alpha is for t tends to minus infinity, this tends to 0 for t tends to minus infinity. For t tends to minus infinity, only if real part of s plus alpha is less than 0 implies real part of s is less than minus real part of s is less than minus infinity, alright. I am sorry, real part of s is less than minus alpha, and therefore, this is your ROC. Okay. And therefore, the Laplace transform in this case of e raised to or minus e raised to minus alpha t u of minus t, this has the Laplace transform 1 over s plus alpha if real part of f s less than minus alpha. Okay. And this is therefore the ROC or the region of convergence. And this can once again be represented in the S plane as follows. You have the real axis, you have the imaginary axis, and now the ROC is the real part of S is less than minus alpha. So, which means you will have your ROC is the entire S plane that is less than minus alpha without including the line that is minus alpha. So, this will be the ROC that is real part of S less than minus alpha. Okay. And therefore, what you have is sigma, this is the j omega axis, and this is the S plane representation of the ROC. So, this is the ROC of minus e raised to minus alpha t times u of minus t. Okay. And now therefore, what you observe is both the signals, both e raised to minus alpha t u t and minus e raised to minus alpha t u minus t both have the same Laplace transform. In fact, if you look at this, these are two distinct signals, correct. So, two distinct signals you have e raised to minus alpha t u t has the Laplace transform 1 over s plus alpha, and e raised to minus alpha t u minus t also has the Laplace transform 1 over s plus alpha, but notice that the ROCs of both are different. So, the ROC of the first is real part of s greater than minus alpha, and the ROC of the second is real part of s less than minus alpha, and therefore, so they have the same Laplace transform but different ROCs. So, same Laplace transform but different . So, these are the same Laplace transform but different ROCs, alright, and therefore, for the Laplace transform to be unique, the ROC must also be specified as part of the Laplace transform, and this is important to distinguish. Not enough to just mention the expression. For the LT Laplace transform to be unique, or the inverse Laplace transform, okay. So, for the Laplace transform, or to determine the signal from the Laplace transform uniquely, correct, for the Laplace transform to be unique, ROC must also be specified as part of the, must also be . So, for the Laplace transform to be unique, the ROC must also be specified, as part of, ROC must be specified as part of the Laplace transform. Let us now proceed to compute the Laplace transforms of some popular signals, and when you come to the popular signals, one of the most important signals, two of the most important signals for, of course, for the analysis or to understand the behavior of LTI systems are, of course, the impulse, unit impulse, and the unit step function, okay. So, let us look at some of the Laplace transforms. The Laplace transforms, now the unit impulse function, okay. So, let us look at the first one. The unit impulse function, the Laplace transform of this, of course, we have xt equals delta t and xs equals, well, integral minus infinity to infinity delta t e raised to minus st, okay. This is integral dt equals Laplace transform of del t, and this is simply e raised to minus st evaluated, remember, integral delta t integral minus infinity to infinity delta t e raised to minus st dt is for any function, the function evaluated at t equal to 0. So, this is e raised to minus st evaluated at t equal to 0. So, this is equal to 1 for all s. So, there is the region of convergence is all s, in this case ROC equal to minus infinity, that is equal to all s, that is all values of s in the imaginary plane, that is real part sigma minus infinity less than sigma less than infinity and minus infinity less than omega less than infinity, covers entire s plane is the region of convergence for this impulse function, okay. So, this is entire ROS or entire ROC. So, So, this is the entire, or sorry, and the ROC is the entire S plane, that is what I mean to say. ROC equals the entire S plane for the unit. Now, let us look at the unit step function. Now, for the unit step function, okay, x of t equal to ut, and the Laplace transform of ut equals minus infinity to infinity u of t e power minus st dt, which is of course, since ut is only non-zero for t greater than or equal to 0. So, this is integral 0 to infinity e power minus st dt, and ut equal to 1 for t greater than or equal to 0, which is, well, e power minus st divided by minus s evaluated between the limit 0 and infinity. Now, e power minus st tends to infinity tends to 0 only if s is greater than 0. So, or real part of s is greater than 0. So, this is 0 minus, and at 0 this is e power minus st is 1. So, this is 1 divided by minus s, but this is 0 only if when real part of s greater than 0, and therefore, this is equal to 1 over s for real part of s greater than 0, and this is basically the ROC. This is basically the this is basically the ROC of this. Okay. So, this is basically the region of convergence for ROC for unit step. So, this is the LT. In fact, we cannot say this is LT because LT is the complete thing, it is the expression plus the ROC. So, this is basically your ROC, or also just to write it once more, this is the region of convergence. Okay. So, in this module we have basically looked at an important concept, that is the definition of the Laplace transform, which gives us the transform domain representation of several signals, which is very useful to understand the behavior and properties of signals as well as systems. Okay. We have looked at the definition and we have looked at examples for the Laplace transform and realized that the region, it is also, in addition to the transform for a given signal, it is also important to specify the region of convergence to uniquely determine the signal given the Laplace transform. Okay. So, we will stop here and continue in the subsequent modules. Thank you very much.